All right, I guess we can go ahead and get started. So this is, again, another piece of joint work. This is a collaboration, actually, between myself and Dr. Jacob Matura, based out of Lublin, Poland. Like I was mentioning earlier, Jacob is unable to be here, so I'll be presenting on his behalf, where we're talking about cardio-oncology, a data-driven approach to risk prediction. Just making sure everything looks good. Great. So this project that we've been working on over the past year or so involves kind of this background that in this landscape of cancer research, as well as the intersection of cancer research with cardiovascular health, is that these are two massive leading causes of mortality globally, and cancer survivors on average face a 2 to 6-fold times higher risk of cardiovascular events due to a variety of different risk factors as one receives cancer care and treatment. And so what we have been looking at right now is thinking around, as someone who receives or encounters a myocardial infarction event, a heart attack, and then goes on to subsequently receive cancer care, our question is how well we can develop and validate an explainable algorithm to predict another myocardial infarction event taking place after this cancer treatment and diagnosis. So some of our objectives and key goals here has been looking at identifying the most significant clinical predictors of recurrent myocardial infarction, creating a transparent, reproducible pipeline for this entire sort of analysis being done in the Julia ecosystem and Julia Health ecosystem, and working with Jacob Matura's team of clinical experts alongside of kind of the more computational side of things here, because as a whole, this collaboration encompasses working with Dr. Jacob Matura, who's not only a technologist, but also a medical trained physician, and his group of individuals who are also medical trained physicians or attending physicians over in the National Information Processing Institute over in Poland. And then also here in the United States side is myself and Professor Justin Mandrides, who is a mathematician and statistician at Northeastern University. So between these collaborations, we've been kind of threading the needle to figure out what makes most sense from a clinical side, a mathematical side, and implementation side. So to speak of our approach, is that as we've been working with observational health data, actually very similar to the data that we were just talking about with patient medical claims and electronic health records, is this question of data heterogeneity. Because once we start exploring these different sort of populations, we very quickly see how patient populations can change and evolve over time, as well as just in general when we look at a nationwide scale. The reason for this in particular is that we're working with a 35 million patient database that comes from Northeastern University to actually explore and recognize what sort of patient cancer populations that we have across the United States represented by this data. And here, we're actually using a bit of a hybrid approach, because while we are using tools from the Julia Health ecosystem, we're also using other tools from the OHDSI ecosystem, which is the Observational Health Data Sciences and Informatics Consortium. It's a bit of a mouthful, so they go by OHDSI. And to actually talk about how we're doing that is, let me pull up an example of an OHDSI tool called Atlas. So Atlas provides a one-stop shop for both technologists and clinicians to actually allow you, and I'll zoom in just a little bit, to allow you to define very comprehensively a definition of disease for a population that you most care about or are interested in. So in this particular study, we actually have gone through and defined over 40 different populations based off of conditions, prescriptions, and diagnoses individuals have received over the course of their care in this data set that we're working with. So to give you an example, so this is an example for kidney cancer. We're looking for any condition of, in this case, kidney cancer. So shown here just very quickly is like some various types of kidney cancer diseases or definitions that are diagnosed. And we also include what are known as descendants of these concepts. This is a whole nother discussion, but oftentimes in clinical ontology, you have these kind of high-level definitions of disease, but then you have multiple different subtypes of these definitions of disease, and very specific ones related back to a particular disorder that you're interested in. And so as a result, you can end up defining your definition of disease and report this definition of disease in either plain text, shown here, JSON, or SQL. And this is using the OHDSI tool, Atlas, to do all of this. Now, you might be wondering, Okay, that's great. We have this tool. Now, how do we actually bring it into Julia and actually start doing our analysis? So for that, I'll switch over to a very small, brief demo here. So give me just a second. So what we can do is we can go ahead and say using HealthBase. And this is a package within the Julia Health ecosystem that provides a lot of convenience functions. We can load in drwatson.jl. And so you can see that the extension for HealthBase, or the extension for Dr. Watson in HealthBase, has been loaded. We can go ahead and initialize a study. So I'll say initialize study, and we'll call it demo study. We'll go ahead and put in my username for GitHub. And so it'll just take a second. So it's using Dr. Watson under the hood to kind of provide a really nice, easy to use interface to actually create very quickly a skeleton for a study that we want to run. So now we have this full study defined. We'll go ahead and add a development package that will be released very soon called Odyssey API that allows us to actually pull down the sort of clinical information that we want from Atlas. So we'll go ahead and say using Odyssey API. And now what we can do is we can say, let's download the definition for kidney cancer. So right now, this is the value for kidney cancer as per Atlas. That's how it's stored. So I can say download cohort definition, throw in that ID. And then there is a convenience function in HealthBase called cohorts directory if you're working with an observational study. And what this will do is it will go ahead and send an HTTP request under the hood using an API built around Odyssey API and Atlas itself, and gives us actually that JSON representation of the cohorts that we'd be interested in. And so if we want to, we can jump over here, go into our cohorts directory, and look very quickly to see, like, behold, at the top, third line, it says kidney cancer, and we can automatically automate all of our workflows from the GUI setting, working with clinical partners, and bring it right into Julia to work with this. Now, what I'll pause kind of here is to say that at this juncture, you might say, like, we have our definition. How do I parse this? Well, there would be additional tools such as, and I'll give you an example of this from HealthBase.jl's documentation. There are additional tools such as Odyssey Cohort Expressions that after you've downloaded your definition of disease, you can go ahead and translate this particular JSON representation into FunSQL, which is a domain-specific language written in Julia to parse out SQL expressions. But in this case, we use it to actually translate that JSON representation of a cohort into SQL itself. And then we can actually execute this cohort definition or this patient population definition against a patient database. And this is just an example to show, like, how it could be done. So switching back to the rest of our presentation here, that's been kind of our process where we've been taking HealthBase to create a single Julia-based processing ecosystem. We use SQL under the hood, kind of under the guise of this Atlas tool. And we collaboratively work together both with clinical partners and computational scientists to define what is the definition of disease that we're most curious about. And finally, we move to, I'll kind of skip ahead just for sake of time. We skip to our modeling strategy, which is using things like machine learning in Julia's ecosystem, or the MLJ package, to look at things like XGBoost and some other tree-based models, as well as probabilistic graphical models coming from Genie, which is a separate software from Genie.jl. But we're using that as well as part of our pipeline here once we have defined our 43 different cohort definitions to then take the data forward and see how we can actually define and work with this prediction problem. To kind of wrap up, to say where we're at with the current status is that our process, our pipeline has been successful. We're able to work with these data definitions. The biggest hindrance right now is still making sure that these clinical definitions are fully matching and mapping to exactly what the clinicians are looking for, expecting to see with each population that we generate. This is not a problem of the actual tools being wrong, but rather just how we're defining our disease as both a clinician and computational science team. But it's a great power and capability that Julia Health provides, as well as some of these other tools to actually work with collaboratively in a same shared environment to achieve a common goal, in this case, doing cancer prediction. And so in short, that is where we're at. Here's our references for this presentation. And again, huge thank you to Jacob Matura and Justin Mandrides for supporting this work. Okay, I think there's time for maybe one question, if anyone has any questions. Okay. Then we'll move to our final talk, which is also going to be me floating up here. Hang on just a second.